So, as you all know, I'm presenting problem number 1, sound thermometer, and I think that's a quite interesting topic because we all have an ability that we are not aware of. We can hear the temperature of sound and the sound of temperature. So, the question reads as follows: why is a method to obtain the temperature of fluid by listening to the sound emitted when it is poured into a cup? Set precision, accuracy, and the limits of the method as well as the important parameters of the fluid. So this task gives us already a nice guideline how to structure our approach or our solving of the problem. First of all, we have to make quantitative explanation and measurements, finding reliable factors. So these are reliable factors that we need to use later for our thermometer. The second thing is to develop a theory, and the third thing is then finally to make our device and give the accuracy and precision. So first of all, how does this work in general? So we have to distinguish between how is sound produced and what is the difference when we change the temperature of our water. So sound in general is produced when we have a surface that is vibrating. In our special case, it's especially the bubbles that are produced and the resonance frequency of these bubbles that lead to the sound that first of all lead to a pressure wave. The pressure wave is going to travel through the liquid, through the medium, the air, to our ears, and that's what we hear. So what changes if we change the temperature of our fluid? This is quite obvious here. We state it a bit more precisely. The density and the viscosity will change. And the exact way how it changes you can see in those diagrams. So I assume, okay, viscosity and density might have an important impact. Besides this, we also have the creation of more and smaller bubbles if we have higher temperature of our liquids. And also we heat our medium, so we change the vapor around when we pour the hot water into a cup. So how does our experimental setup look like? This is what we imagined, what we thought about, and for us it was important to control the way we splash the water into our container. So that's how we just thought about our device. This is how it looks in reality, and you see that we just always try to have, for example, a fixed distance between the microphone and the bucket or the cup, and that we have made all the experiments with 2 different cups. So what are the important parameters? Most of all, of course, the temperature that we need to change, the distance that we just try to keep constant the whole time so that we have no change of amplitude only due to change of our setup. Then, of course, the velocity of the water, the size and the form of the cup that have an influence of the sound that we are recording, and the external sound sources like the noise. So what experiments did we start with? We started with measurements from 1 to 95 degrees and 5 degree steps. So we made 10 measurements of every 5 degree steps. And also we added current power to water that was around 20 degrees so that we can distinguish between the effect of the real temperature and the effect of the viscosity change. So first of all, what do we see when we analyze our spectrums of the measurements from 1 to 95 degrees? Can be summarized in here. What we can already see quite well is that the sound level changes with the change of the temperature. So when we plot it a bit more visible, we see that when we have, for example, a comparison between 20 and 90 degrees, we have a much higher sound level when we have a higher temperature. This also is consistent with different temperatures, and this factor we now can already use for finding out the method, because also when we put it in our 2 different cups, we see this correlation between the temperature change and the sound level change. So we could now use this for designing a thermometer, but as you see, it's not really accurate. So we can already calculate our temperature, but we're not satisfied with it. So let's try to find other parameters that change when we change the temperature of the water. First of all, when we go deeper into analysis, we find out also the frequency, but not all frequencies, so the general mean frequency changes. But first of all, we find out that the delta frequency changes. So we all know if we pour water into a cup, we have a different frequency depending on the filling height. And this delta frequency, so the difference between when we start doing it and when the cup is nearly full, this delta frequency changes with temperature. So we can see this correlation. For now getting rid of this changing filling height, and that's a consequence, the change due to the time that we are pouring the water into the cup, we do a similar experiment but not the same. So we start our experiment with an already full cup, and then we just make like a running over experiment so that we get rid of this filling height. When we do this and examine again our recordings, we can find out that we really have also a change in our mean frequency. So we can see that also our mean frequency changes. So to sum up what we found out due to our experimental setups, we have a shift of the whole amplitude, we also have a shift of the frequency and of our delta frequency. So we can use all of those three factors for now finding our method. First of all, we want to develop a theory. So regarding to our theory, we assume that we have perfectly spherical bubbles. So as I already said, we think that the bubble formation and the resonance of the bubble is the most important factor. So we can use the Minihertz formula to simulate this or to calculate this. And what is important is that we also don't have only a harmonic oscillator due to the bubbles, but that we have a damped harmonic oscillator. So we have to take damping into account. These are temperature or thermal damping and radiative damping. So when we take this into account, we finally get to our pressure equation. So with this pressure equation, we can find out what pressure we have dependent on the distance from our bubbles that are created. So we have to set in despite Ft, F0, because the Minihertz formula assumes that we have an infinite volume. But of course our cup can't have an infinite volume of water. So that's why we have to improve this approximation. So we finally get to our equations of our pressure waves. And of course, what now is still missing is that we don't have spherical bubbles, as we assumed before, but that we have more, not only spherical bubbles, but bubbles that have really different shapes. And because we have a more complex and quite a bit chaotic system when we pour water into a cup, these different shapes are produced, so we need a more complex equation. This equation we finally use to simulate our sound. So with this simulation, I now come to the concluded method. So what is my thermometer based on? We base it on both. We base it on our measurements and as well on our theory. So we did some more measurements, 50 measurements for every 5 degree steps. And on the other side, we have our theory. And with the theory, we can simulate the sound depending on the temperature of the liquid that you put in. We compare the two different results that we get from this, and when we have the kind of give to our program, we give the combination of those both. The program has an idea how should our sound wave look like on 5 degrees, 10 degrees, 15 degrees. Then we record our sound, and the program can compare the recorded sound with the stored sounds and find the best sound wave that is fitting. So when we look on this plot from the temperature of the water that we just measured with a normal thermometer and our reduced temperature, we see that it's quite already a nice approximation that we achieve. But what limits do we have? So first of all, what is good is that we take non-spherical bubbles into account, that we have different parameters, settings that are possible. For example, if I want to change the cup, or if I want to change, for example, the viscosity of my water, I can calibrate my whole system U. It will take some time, but I can do so, and that's why I can use the method also for different setups, not only for one. So, but the limits, of course, are that the industrial thermometers are quite better or performing better than our thermometer. Also, the programming speed is not really high, so it already takes a lot of time now. And we only have the 5 degree step, so we of course could do it with every degree, but it would take much longer. And of course, we also have the noise that we recorded with, but we have some ideas to improve this. Yeah, so maybe the last point before coming to the conclusion. It's that we looked again at our task, and we see that the task says that it's by listening to the sound. So we just thought about how do we define listening. Because when we just have a computer program, it's not really maybe listening. If we define listening as a human ability, we have to make some more limits, because we as humans, we can only hear in a special range of frequency, and also we don't hear the double decibel scale with a higher tone, but that's why we need to use another scale, the Mel scale, because the Mel scale just records or says how we human beings hear. And this is what we plotted also, and we see that also with the Mel scale we see some differences. So yeah, that's my conclusion, and thank you for your attention.